Ooh, yeah, that's a nice little bit of glass there. All righty, good morning, lads and ladies. Welcome back to Calc 2. Sorry you caught me trying to pull a little bit of glass out from my big toe. Oh, none of y'all are here yet. Is this the right meeting? 312.004, did I post it in the right place? Oh, they don't have it yet. All right. Supposed to. Oh, God damn it. Oh, it's not glass, it's a piece of wire. There she is. Oh, that should be good. Okay, lads and ladies, sorry about that. I got a little piece of copper wire stuck in my foot and distracted me for just a second. But as folks start filtering in, today we are going to change topics. So good news, we're done with infinite series. No more power series, no more convergence tests. You have made it through what is by far the hardest part of not just this course, but the entirety of the calc sequence. So it is pretty much a universally acknowledged thing that Calc 2 is the hardest of the calc classes. And the reason for that is precisely the stuff you've been slogging through these last few weeks. So the good news is no more power series, no more convergence tests. That stuff is done. You have learned all I require you to learn regarding series and sequences. So take a deep breath, pat yourself on the back. No more capital sigmas to be afraid of, at least, you know, except on the exam. But today we're going to start talking about something else that's near and dear to my heart, and those are parametric equations, or curves defined by parametric equations. So that's where we're going. Let me turn on my document camera. We can get right into it. Oh, come on. No, why aren't you seeing it? It's booted. Oh, there it is. Just here to initialize it. All right, there she is. So as promised, no more capital sigmas. We are done with power series. We are done with sequences. We are done with convergence tests in general. In this last week, I have a few kind of disparate topics that we need to talk about because, well, they're important. Parametric curves, which is what we're going to be talking about today, or parametric equations, curves defined through parametric equations, are hugely important in Calc 3. They're also very important if you were to study something called complex analysis, which might sound a little bit foreboding, but if you're going to go into control systems, dynamics, differential equations, anything like that, you'd be surprised how much thinking in terms of complex variables is useful. And one of the requisite skills for doing most complex analysis is understanding parametric curves. So this is MAC2312, section 004. It's a lecture, and today is the 20th of April, 2021. Today we're going to talk about parametric curves. Sometimes people also call this parametric equations. It's really two sections, 10.1 and 10.2. And then on Thursday of this week, we're going to talk a little bit more about parametric curves, but mostly about polar coordinates, which is a totally different thing. Those are sections 10.3 and 10.4. And then we will be done with the semester. That will be all of the material. Recall, of course, that exam 3 is going to be a take-home exam. I will give that out on Thursday following class, and I will have that be due on the day of the final. You will need to submit it on Canvas. We'll go through the instructions very carefully on Thursday. I don't want to burn any time, so let's just get right into it. Some plane curves can be expressed as functions of x. These are those which pass the vertical line test. And you know what these look like. These are things like x squared, or sine of x, or cos of x, all of your trig functions. All right, so here y is equal to x squared. That means every point on this curve, the y coordinate is the square of the x coordinate. In other words, this is all of the form x comma x squared. Over here, if this is y equals the sine of x, then every point along this curve is of the form x comma the sine of x. Some plane curves can be expressed the other way, as something like x equals f of y. These generally don't pass BLT. They don't generally pass the vertical line test, but these are things like those sideways parabolas that we saw at the beginning of the course when we talked about areas between curves. So this could be like x equals 1 minus y squared. Or you could have something else like what should we say? Here, let's be silly about it. How about something like this, where you have x equals the cosine of y. Kind of the equivalent idea to the idea above. Your horizontal axis is still your x-axis. Every point along this curve would be of the form 1 minus y squared, comma y. Every point along this curve would be of the form cos y, comma y. So these are all things that we are familiar with, that we have worked with throughout the semester. I'm just kind of reminding you explicitly this issue of the points on the curve being of this form. That's what it means to say you're on the curve y equals x squared. It means that every point you've got an x, and then the y value is the square of that x. That's what this equation means. Or saying y equals the sine of x. That means every point is x comma y, where y is the sine of x. And if you swap the roles of x and y, you get stuff like this. So here you would think of x as the dependent variable and y as the independent variable. So y is the thing that's allowed to roam free, and then x along this curve has to be of the form 1 minus y squared. That's precisely what this means. And the same thing over here. Y is allowed to roam free, and the x's are all the x's along this curve are the cosine of the y value at that point. But some curves can't be expressed in either of these ways. Think of the unit circle. The unit circle passes neither the vertical line test nor the horizontal line test, whether you're looking with respect to x or with respect to y, this is not a function. Or more generally, you could have something super duper complicated. Right? You could have something like this. Who knows? And instead of being a connected curve, maybe it has a starting point and a stopping point. So in both of these cases down here, you don't pass the vertical line test, meaning y is not a function of x, and you don't pass the horizontal line test. That's the second one. It's another way to say that. Passes the horizontal line test. That means x is a function of y. But down here, again, neither of those things are true. We know that there are implicit expressions for the unit circle, like x squared plus y squared equals 1. That's an equation, and the points that satisfy that equation are going to give you the unit circle. Conic sections are nice like that, and there are plenty of other curves like that. But what about wonky ass shit like this, where it appears that there's no direct connection between the x's and the y's? Is there any way to express these things in terms of an equation or a collection of equations? And the answer is yes. Parametric curves, or parametric equations, are an especially useful tool for things like these. They can be used in the other contexts too, but they are especially useful in contexts like this. So that's sort of the motivation. Some curves, y is a function of x. Other curves, x is a function of y. But then there are way more curves that live totally outside of either of those families. In fact, if you give a 5-year-old a pen and you say, hey, go draw on this paper, odds are you're going to end up with something like this that passes neither the vertical line test nor the horizontal line test. Remember what those both mean. If you pass the vertical line test, that means y is a function of x. That means there is, in theory, some expression, f of x, that y would be equal to along this curve. In other words, if you pass the vertical line test, there should be some way of representing that curve algebraically that is solved for y. If you pass the horizontal line test, that means there should be some way of representing that curve algebraically that is solved for x. If you pass neither, then there is no way to write x equals blah, blah, blah involving y, or y equals blah, blah, blah involving x. You either need an implicit expression like this, x squared plus y squared equals 1, or something else. And the something else that works for this works for everything else on the page, and those things are called parametric equations. So how do we do this? Well, it turns out that there are a few ways to come at it. Now some backing sheets here, so I'm going to grab a few more pages. But before we talk about direct attacks, how to take a curve and give it a parametric equation set, or how to graph a parametric curve, we just need to know what these are. So definition. A parametric curve is a curve in the plane defined by two equations, usually x equals, I'll call it f of t, and y equals, we'll call it g of t. But of course, we could use any other labels we wanted for those. I could just call them x of t and y of t if I wanted to. And usually, a specified domain for the variable t. And the term variable here, it means parameter. Parameter and variable mean the same thing. So rather than having y equal f of x or having x equal f of y, you have both x and y independent from each other, but both dependent on this variable or parameter t. Usually we think of t as time. Usually we think of these curves as paths that objects move around on. It's a useful metaphor, but it's not necessarily the only way to think about these things. So let me show you an example and the basics of graphing one of these things. Let's sketch the graph. How about of the parametric equations x equals t minus 1 and y equals t squared. Very simple, right? We're going to sketch these in the xy plane. But our variable is t, and we think of t as, again, being like time. I'll specify a time domain. Let's say t comes from the closed interval about 1 to 5. Or you could also write this as 1 is less than or equal to t is less than or equal to 5. These mean the same thing. So kind of at the college algebra level of thinking, the way you sketch a curve is to make a table of points, right? So I'll have a t column, an x column, and a y column. This table is going to have 3 columns. And I'm going to let t run from 1 to 5. I'll just plug in the integer values, 2, 3, 4, and 5. When t is equal to 1, x is equal to 1 minus 1. That's 0. And y is equal to 1 squared. Okay, that's 1. So this tells me that the point 0, 1 is on my graph, and it's associated with the t value t equals 1. I'm going to fill out the rest of this table. When t is 2, x is 2 minus 1, which is 1, and y is 2 squared, which is 4. When t is 3, x is 3 minus 1, which is 2, and y is 3 squared, which is 9. When t is 4, x is 4 minus 1, which is 3, and y is 4 squared, which is 16. And when t is 5, x is 5 minus 1 is 4, and y is 5 squared is 25. So if I don't know anything else and I want to sketch the graph of some parametric equations, I just make a table. Let's draw the graph now. I've got a bunch of points. In this setting especially, it's a good idea to label your axes. One of the things that people really struggle with here is that there is no t-axis. Even though t is your variable, t doesn't actually show up anywhere in the graph. The ordered pairs are 0, 1, 1, 4, 2, 9. They're all just x's and y's. All right, so let's start. I'm going to label this up here as 25. I'm going to label this as like 1, 2, 3. How big do we go? Up to 4. 4. So the point 0, 1 would be like right here. The point 1, 4, say it's like right here. The point 2, 9, like right here. 3, 16, right about there. and 4,25. Really, my scale is a little bit up. Should be like right about there. So here's my starting point, also sometimes called the initial point. That's the point on your graph associated with the smallest t value in your time or t interval. And over here, I would call this my ending or terminal point. And it might be a little bit hard to see, but the curve that we're sketching here, modulo my bad art, is actually a parabola. I know it ended up looking kind of linear, but it is. It's a parabola here. Look at these ordered pairs: 1, 9, 1, 4, 2, 9, 3, 16, 4, 25. So the whole parabola would look like this. But my parametric curve just goes from the starting point to that ending point. And it has an orientation. As t increases, I'm going this way along the curve. And we like to draw those in with little arrows like this. So if you don't know anything else about a set of parametric equations, you can draw the graph just by plotting points. Another thing you can do is called eliminating the parameter. So if we want to, we can try to find the normal xy equation for this curve by, it's called eliminating the parameter t. What that means is working with these two equations to somehow get rid of the t's and just get an equation in terms of x and y. So what would that look like here? You can take one of those equations and solve it for t. We know x here is equal to t minus 1. And if I solve that for t, I get x plus 1 is equal to t. So our first step is, if we want to eliminate the parameter, solve one of the equations for t, and then you take that and plug it into the other one. So y, which is t squared, would be equal to x plus 1 quantity squared. And that is actually our parabola here. This is y equals x minus 1 squared. All right, sorry, x plus 1 squared. So our graph above is a portion of the parabola y equals x plus 1 quantity squared. So I guess the whole parabola should really come down here and then dip back up, something like that. But have this root over here at -1. I want to get us just a little bit more practice graphing parametric curves, some more examples that are a little bit more exciting. Show you a few other examples of eliminating the parameter, because sometimes that can be a bit tricky, especially if there's some trigonometry involved. And then we're going to see how you can do calculus with these parametric curves. Questions on where we got this table, those points, or the picture from here? Okay. Let me take an example from your textbook. They have some good ones in there. T squared minus 2t and t plus 1, sure. Sketch parametric curve defined by the equations x equals, what was it? T squared minus 2t and y equals t plus 1. Let's see, did they specify a time domain here? They didn't. So sometimes they'll specify a time domain, like I did on the previous example. Sometimes they won't. If there is no time domain specified, like 5 is less than t is less than 20, then you can plug in whatever you want for t. It's implicit if there is no specified time domain that the time domain is negative infinity to infinity. And I'm actually going to write that in here. Just like on our last example, we're going to make a table of values. It will start at like -2, -1, 0, 1, 2, just to give us a little feel for what's going on. And then we fill out the table. So when t is -2, what is x? Well, it's -2 squared minus 2 times -2. -2 squared is +4. And then from that, we're going to subtract 2 times -2. So 2 times -2 is -4. I take +4 and I subtract from that -4. I get, here, we'll write it down. So -2 squared minus 2 times -2. I don't want us to lose things in the negatives. That's 4 minus -4, which is +8. And y is -2 plus 1. That's just -1. When t is -1, we'll have -1 squared minus 2 times -1, which is 1 plus 2, which is 3. So when t is -1, x is equal to 3. And y would be -1 plus 1 is 0. When t is 0, x is 0. 0 squared minus 2 times 0. And y would be 1. When t is 1, x would be 1 squared minus 2 times 1, and 1 minus 2 is -1. And y would be 1 plus 1, which is 2. And when t is equal to +2, we would have 2 squared minus 2 times 2, that's 4 minus 4, that one is 0. And y would be 2 plus 1 is 3. So let's plot these points. I'll mark this over here as 8, so this is like 4. Y values are pretty small. I'll mark this as 3, 2, 1, -1, -2, -3. And again, it's useful to label the axes to remind yourself that there is no t-axis, just x's and y's. So the graph is just x's and y's, even though it's all coming from t's. I've got the ordered pair 8, -1. Then I have the ordered pair 3, 0. So 3 would be about here. Then I have the ordered pair 0, 1. Then I have the ordered pair -1, 2. So -1 would be like right here. -1, 2 would be right about here. And then the ordered pair is 0, 3. So from these, you can probably start to see what's going on. We've got a curve doing something like this. Just for gits and shiggles, let's go 1 or 2 more here. So when t is equal to +3, we would have 3 squared minus 2 times 3, which is 9 minus 6, which is 3. And y would be equal to 3 plus 1, which is 4. So the next ordered pair on my graph is 3, 4. We have some symmetry going on. And right around here would be 3, 4. And if you sketch in the curve, if you connect the dots, you see something like this. And since the t's are running from -infinity to infinity, we can see as the t's go further towards -infinity, we would be going further out here. And as the t's go further towards +infinity, we would be coming further out here. So what we have here is a sideways parabola. This is the point associated with t equals -2. This is the point associated with t equals -1. This is the point associated with t equals 0. This is the point associated with t equals 1. This is the point associated with t equals 2. And this is the point associated with t equals 3. So you see as t increases, -2, -1, 0, we're traveling in this direction along the curve. So the orientation arrows would go like this. Every parametric curve has an orientation, and you need to include those little arrows in your sketches. Turns out that the orientation of your parametric curve matters a lot. Later in Calc 3, you'll be doing integrals over these parametric curves. You'll have some higher dimensional surface that lives above this curve. And you'll take an integral of that surface along a curve like this, and the orientation will affect the sign of the answer. So it is an important thing. Are there any questions about how we got this picture? Okay. What I'd like to show you now is that we can eliminate the parameter here. To get the normal xy equation. Since we've seen the graph, we know that y here is not a function of x. This does not pass the vertical line test. So I'm not expecting to get like y equals x plus 1 or something like that, like I got last time. I'm expecting here to get something like x equals some combination of y's. So it'd be easier to start by solving this equation for t. Remember, to eliminate the parameter, most of the time you're going to solve one of the equations for t. So here, y equals t plus 1, that's easy to solve for t. I can subtract 1 from both sides, and I get y minus 1 is equal to t. And then I can plug this into the x equation. So x, which is t squared minus 2t can be rewritten as y minus 1 quantity squared minus 2 times y minus 1. And we could FOIL this out and do all the stuff we want. That would be y squared minus 2y plus 1 minus 2y plus 2. And we distribute everything. So we get y squared minus 4y plus 3. Any questions about how I got this expression? Okay. I'd like to show you something in Desmos now. First, I'm going to graph that curve using this equation. And then I'm going to show you how to put the parametric equations in. X squared minus 4y plus 3. Looks familiar, right? This is our guy. 8 comma negative 1, 3 comma 0, 0 comma 1, 1 comma negative 2, 0 comma 3. That's our guy. If I want to put in the parametric equations, we type them like this, but instead of the x here, I type the x equation, t squared minus 2t. And instead of the y here, I type the y equation, t plus 1. And now you see this little blue piece showing up here. That blue is the portion of this parabola that would be traced by my parametric equations if t is allowed to run from 0 to 1. If I let t run from -2 to 2, you'll see in blue there the portion that we originally had, because those were the t values that we originally used. Does everybody see that? So to graph a set of parametric equations or a parametric curve in Desmos, enter them as ordered pairs. Parentheses, the x equation, comma, the y equation. And then Desmos is smart enough that it'll ask you for your time interval. I could give this in terms of another parameter, s, and then ask for a slider. And then you can watch a point move along this curve. And that's what I mean when I say we usually think of the parameter as time, and we usually think of these curves as being paths that particles or objects move along. The only reason I'm using the variable s here is because I've already used the variable t for something else, and Desmos would get confused. You can change this to run consistently in one direction. You can change the bounds, like I could ask it to go from -5 to 5, taking steps of 0.1, something like this, and then you just see it traced to the positive orientation, which is nice. So you can imagine there's lots of applications in physics where we care about particles in motion, and that's certainly true. A number of problems in physics too, the electromagnetism class, they won't usually be couched this way, but oftentimes they could be. So graphing parametric curves is not terribly hard if you're given the equations. You can just make a table, or you can eliminate the parameter to get your regular xy equation and then graph that thing. The trick is, let me turn this off, that if I only wanted the -2 to 2 portion of the curve, the portion of the curve associated with the time values -2 to 2, if I just eliminated the parameter and graphed the red guy, I wouldn't know which portion I'm using. I wouldn't know which part of this curve is associated with these t values. I also wouldn't know the orientation. So doing this by hand is actually an important thing. Doing it by hand is what will teach you the orientation, and it also ensures that you get the right part of the curve. But eliminating the parameter can be a great way to check your work. Questions on this example? As you work the homework this week, it's very important that you draw these fucking things by hand. I will be making you draw these things by hand on the test, both the last midterm and the final. You won't have access to graphing utilities. I will need to see all the work that leads to this picture being done by hand. So please practice doing this as I've done it here. That way you'll actually develop the skill. Okay, so yeah, I guess it's time to talk about these things. I would like to do one more example here. Same stuff, sketch a parametric curve. Let's say x equals cos t and y equals sine squared t. And here I'll let t run, how about from 0 to pi? So I'll make my table. Let me pretend like we're back in algebra class. I'm going to pick some t values that are nice here, right? Like I wouldn't want to use t equals 0, 1, and 2 because I'm dealing with trig functions here. And so I'm going to use 0, maybe pi over 4, pi over 2, 3 pi over 4, and pi. Those are some nice trig inputs that are between 0 and pi. When t is equal to 0, x is the cosine of 0, which is 1. And y is sine squared of 0. Well, sine of 0 is 0, so 0 squared is still 0. When t is equal to pi over 4, cosine of pi over 4 is root 2 over 2. And sine is also root 2 over 2. So sine squared would be 2 over 4, or 1/2. When t is equal to pi over 2, x is the cosine of pi over 2, that's 0. And y is the sine squared of pi over 2, which is 1 squared, which is 1. So you see, as t increases from 0 to pi over 2, the x's are getting smaller. That means we're walking to the left. And the y's are getting larger. That means we're walking up. When t is 3 pi over 4, the cosine of 3 pi over 4 is negative root 2 over 2. And the sine of 3 pi over 4 is the square of that, which is again 1/2. And then when t is equal to pi, the cosine of pi is negative 1, and the sine of pi is 0. So 0 squared is still 0. Here's the table filled out. Let's draw our picture. Since these are trig outputs, everything is going to be between -1 and 1. So we want to choose our scales wisely. I'll make this over here, say -1, and similar distance over here, call that +1. My y values also run up to +1, so I'll make this +1. I have the point 1, 0, and that is my starting point or my initial point. You want to label those, your initial point and your terminal point. When t is equal to pi/4, we have the ordered pair √2/2, 1/2. We might wonder how big √2/2 is. We can ask as a decimal. It's about 0.7, a little bit bigger than 2/3. So we have like 0.7-ish, 1/2. So here's 1/2 on the y-axis. Here's 1/2 on the x-axis. 0.7 would be like here. So here's your point. When t is equal to pi/2, we're at 0, 1. That's up here. When t is equal to 3 pi/4, we're at the symmetric point to this guy, which would be here. And when t is equal to pi, we're at -1, 0, which is over here. Since I've specified a time domain, that first point, the point associated with t equals 0, is my initial point. And this last point over here, the point associated with t equals pi, would be my terminal point. And the curve looks something like this. Modulo my bad art. And remember the orientation? We started over here. As t increased, we went this way. So this is my parametric curve. Would anybody care to guess the thing we're looking at here? I see we've got something in chat there. This one is not the unit circle. If this was just regular sine of t, then I would be looking at the unit circle. But you notice I haven't drawn this tangent as being vertical here or here. And that's intentional. This is actually not the unit circle. It's something else. Remember, on the unit circle, we would have √2/2, √2/2. Right? Not √2/2, 1/2. It's something else. So the key is going to be eliminating the parameter. And neither of these is nice to solve for t. So I'd like you to look at these equations for a minute and see if there's any relationship you can come up with between y, which is sine squared t, and x, which is cos t. And my hint is use a trig identity. I'm going to replenish my coffee. I will be right back. I want you to think about that. Does anybody see something I could do with this that would allow me to relate it to this? So Nico's answer, while correct, is not going to help us here. It's true we could apply a half angle formula to this. But I did get a message, a private message that's correct. So here, y is sine squared t, which by the first Pythagorean identity is the same as 1 minus cos squared t. And then we compare that to this guy and we go, oh shit, well, cos t is x. So this is 1 minus x squared. In other words, the thing we're looking at here, not to be boring again, is another parabola, i.e. our curve is a portion of the parabola y equals 1 minus x squared. Yeah, this is our guy. This is our guy. What portion? Well, it's the portion whose x values are going from -1 to 1. And that makes sense. X here is cos t. Cos t can only output things between -1 and 1. The orientation is also important. It's traced from right to left. That's a little bit abnormal. Normally we think of curves as going from left to right, but in this case, it's traced from right to left. I can play the same Desmos games, and it can be useful to think of these. Be running from 0 to top. And if we want to watch the particle bounce around in there, we can. Does it not like this for some reason? Oh, I need to turn it on. Yeah, there we go. So here's what this particle is doing. It's bouncing back and forth along this guy. The blue portion is my parametric curve. And it is a piece of this guy. I can fix these to go from 0 to 3.14-ish. That way you'll just see the motion in that direction. Very nice, right? So this is all well and good. We can trace curves. If I give you a curve, like I say y equals 1 minus x squared, can you come up with a parametrization? That's a different issue altogether. What I'm about to show you is something that people struggle with a lot, so I want you to pay extra careful attention. This is actually the part that's going to be super relevant in Calc 3. Finding parametric representations of curves. So if I give you something like y equals f of x, I give you some curve that you know, I can ask you to find a parametrization. So the term is parametrize. To parametrize the curve y equals f of x, we can use, here's the lazy one, this is called the standard parametrization. Now remember what those curves are. If y is equal to f of x, you're looking at some normal function. That's just the set of all points of the form x comma f of x. So if you really want to be like lazy about this, if you're not worried about the parametrization, just let x be t and y be f of t. So if I ask you to parametrize sine x, you could let x be t and y be sine of t. That'll work. The big thing you need to pay attention to is the range that you choose for your x function. You want to make sure that the x function has range all real numbers. So other choices here could be things like x equals the ln of t and y equals f of the ln of t. Or you could use, I don't know, x equals the tangent of t and y equals f of the tangent of t. There's lots and lots of ways to do this. You just need to make sure that the outputs from your choice for the function x, whether you choose x equals t, ln of t, tangent of t, match up with the x values you want on your graph. It doesn't even need to be true that these functions have range all real numbers. Their range just has to be what you want for your x's on the graph. I'm choosing these because all three of these have range all real numbers. So for the appropriate choice of time domain, you could parametrize any curve given as a function of x with one of these three. And I'll tell you a standard question on my exam 3 or on my final, it shows up usually in at least one, is give me two parametrizations of the curve blah, blah, blah. So this is the way you do it. Quick example. Find two parametrizations of the curve y equals 1 over x. And let's specify some particular piece of this curve. I don't want the whole thing, let's say. I just want the piece where 1 is less than or equal to x is less than or equal to, let's say 5. Let's say 5. And you know what? Maybe I'll make this 1/2 is less than or equal to x is less than or equal to 5. That way we get a nice chunk of that guy. So what does that look like? Well, we really should know what 1 over x looks like. Here's 2, here's 1. When x is equal to 1/2, 1 over x is equal to 2. When x is equal to 1, 1 over x is equal to 1. When x is equal to 2, y is equal to 1/2. When x is equal to 3, 1/3, and so on like this. So here I'll say this is 5, and we should be really close to the x-axis there. So here's the thing I'm looking for. So I know this is the graph, y equals 1 over x. I know it continues up like this, has a vertical asymptote there, but I'm not interested in that. I'm just interested in the piece from 1/2 to 5. All right, here's 1/2. We can use the standard parametrization. Which would be x is equal to t and y is equal to 1 over t. Right, just following this rule, x equals t, y equals f of t. Well, here, what is f of x? F of x is 1 over x, right? So if I choose x to be equal to something, to stay along this curve, y has to be 1 over that thing. That's all. And here the t values would be 1/2 is less than or equal to t is less than or equal to 5, because I want my x's to run from 1/2 to 5, and x is equal to t. So this would be one answer. Here is one parametrization of that curve. Another one I could use, I could say x is equal to the natural log of t, and y is equal to 1 over the natural log of t. But now, in order to make sure I'm getting this portion of the curve, I need to make sure my x values run from 1/2 to 5. That means e to the 1/2 would be less than or equal to t would be less than or equal to e to the 5. Because to get this equal to 1/2, you need t equal to e to the 1/2. The natural log of e to the 1/2 is 1/2. So this would be another way to parametrize that curve. And there are many, many more. Questions on this? So on the test, when I ask you guys to parametrize a particular curve, we all know the standard parametrization, and we can all come up with at least one more, right? Just pick your favorite thing here, whatever you want, and then make sure you plug that thing into the equation that defines the curve for your y. All right. Some examples that are less obvious include the unit circle. And whether you know it or not, you actually are aware of a parametrization of the unit circle. If x is the cosine of t and y is the sine of t, then you're going to get at least some portion of the unit circle. Why? Well, what is the unit circle? Remember how the trig functions are defined. Any point here is of the form cos theta comma sine theta. So your x's are cosines and your y's are sines. You can think of the theta here as being t. Right, so this is your x, and this is your y, and this angle here would be t. So your sort of normal understanding of the unit circle really is a parametric representation of the curve x squared plus y squared equals 1. We can verify this by eliminating the parameter. And the trick here is the same as the trick we used on the last example with some trig. It's the Pythagorean identity. X is equal to cos t. This means x squared is equal to cos squared t. Y is equal to sine t. So y squared would be equal to sine squared t. Therefore, x squared plus y squared would be cos squared t plus sine squared t, which by the first Pythagorean identity is 1. So you're along the curve. X squared plus y squared equals 1. This is what's called the standard parametrization of the unit circle. We can't use the standard parametrization trick from the previous page because this curve does not express y as a function of x. It fails the vertical line test. But this term, this particular parametrization of the unit circle is called the standard parametrization. It walks around the unit circle counterclockwise. So the orientation here is like this. As t increases, we run around the unit circle like that. Okay. You'd be surprised how easy it is to generalize this into ellipses, which are fairly complicated in Cartesian equations, right? Regular XY equations. Very simple in parametric coordinates. So I'll show you just a few quick examples here in Desmos. And we'll go from, we'll go 0 to 2 pi. So this is what we just looked at, the unit circle. If I multiply both of these by 4, I get the circle of radius 4, centered at the origin. If I want to shift the circle left or right, I can add 1 or 2 or 3 or 4 to the x coordinates. That will move all the x values to the right, dragging the whole circle to the right. If I want to move it to the left, I can subtract stuff from the x coordinates. And if I want to move it up or down, I can add or subtract stuff from the y coordinates. So here I have a circle centered at -3, -2 of radius 4. The way you go from something like this to an ellipse is just by messing around with one of the coordinates at a time. So let me get rid of this. You saw this a second ago. X of t here is 4 cos t, and y of t is sine t. So the x equation is, it's like the normal unit circle thing, except I've multiplied all the x's by 4. So it's going to stretch everything out horizontally by a factor of 4. If I multiply the y values by 2, it'll stretch everything vertically by a factor of 2. So ellipses are really nice to describe parametrically. And there are some problems in your homework that give you a set of parametric equations for an ellipse and ask you, what's the center? Where are those vertices? What direction is the thing being traversed in? And all of this can be thought of very naturally as kind of squishings and stretchings of the unit circle. Okay. That is our quick and dirty introduction to parametric curves. In the last few minutes, I'm going to show you how to get your normal calculus operations with these things. Surprisingly easy. Differential calculus with parametric curves. If x is equal to f of t and y is equal to g of t, can we find the normal derivative dy dx? In other words, can I find slopes of tangents here? Can I find mins and maxes here? Can I do all the Calc 1 shit in this setting? I wouldn't ask the question if the answer was no. Theorem. dy dx is equal to dy dt over dx dt. Or in the notation I have over here, it would be f primed of t over g primed of t. I'm sorry, shit, g prime over f prime. Fuck. Sorry. You take the derivative of the y equation with respect to time, and you divide that by the derivative of the x equation taken with respect to time. You can kind of think of it like the dt's cancel, even though that's not really what's going on. But this is it. So if you want to find slopes of tangents, you want to find mins and maxes, you want to find locations of vertical or horizontal tangents, this is how it's done. Let's find the equation of the tangent line to that first guy, x equals t squared minus 2t, y equals t plus 1, at the point, what was the point that was on that curve? At the point 0, 3. We know how to find equations of tangent lines. You need a slope and a point, right? That's it. The trick is here that to find the slope, you need to get dy dx. But I don't have y as a function of x that I can straight up differentiate. Y is a function of t and x is a function of t. But for the slope, I just remember that dy dx is dy dt divided by dx dt. So what is dy dt? If I differentiate this y function, the derivative of t plus 1 taken with respect to the variable t is 1 plus 0, or just 1. If I differentiate the x equation to find dx dt, I get 2t minus 2. This is all well and good, but it gives me dy dx as a function of t. Again, not as a function of x. So if I want to find the slope of the tangent line at the point 0, 3, I need to know what is the t value associated with that point. To remind you this picture, here's our curve. The point associated, or the t value associated with the point 0, 3 was t equals 2. Right? 0, 3 came from t equals 2. Well, what if I didn't already know that? So to find the t value associated with the point 0, 3, we solve x equals 0 and y equals 3. Sometimes one of these will produce a unique solution and the other one won't, but it's always wise to at least look at both. If x is equal to 0, that means t squared minus 2t is equal to 0. And if y is equal to 3, that means t plus 1 is equal to 3. The first equation actually has 2 solutions. The second equation only has 1. So right away here, I could get t equals 2 and call it a day. But you can also factor here, you get t times t minus 2 equals 0. So you know that t is either 0 or t is equal to 2 from the x equation. From the y equation, you know t is equal to 2 right away. So t equals 2 is the t value associated with 0, 3. Therefore, the slope of my tangent line is always going to come from the dy dx derivative, but I need to evaluate it at t equals 2. In other words, I need to take this and plug in 2 for t. And if you do that, you get 1 over 4 minus 2, which is 1/2. Hence the tangent line is, well, it's always, we write these down using the point slope formula. Hopefully you remember this from Calc 1. My x0 and y0 are the x and y coordinates of my point, and the slope is 1/2. So this is y minus 3 equals 1/2 times x minus 0. Or if you want, y equals 1/2 x plus 3. Either of these would be acceptable. The other kind of standard game that we play with this is asking you, where are the tangent lines vertical? Where are the tangent lines horizontal? I'm going to take just 2 more seconds of your time to show you this thing so we can start at the right place on Thursday. Finding horizontal and vertical tangents to parametric curves. Recall that the slope of a tangent line is dy dx. And that when you're looking at parametric curves, that's dy dt divided by dx dt. So a parametric curve will have horizontal tangents when m tan is equal to 0. Right? When the slope of the tangent line is 0, that means you have a horizontal tangent line. That's what horizontal tangents are. Horizontal lines in general are lines with slope 0. And this is equivalent to saying that 0 is equal to dy dx. And that means that dy dt is equal to 0, but dx dt is not equal to 0, because dy dx is dy dt over dx dt. So to find horizontal tangents, find your dy dx. It's dy dt over dx dt, and then figure out where the top is 0. Make sure that the bottom is not also 0 there. Then that will be a t-value where this curve has a horizontal tangent. And vertical tangents when the slope of the tangent line goes to plus or minus infinity, which means dy dx is going to plus or minus infinity, which means the bottom is going to 0 and the top isn't. Right, so just like in Calc 1, to find locations of horizontal tangents, you need to know where the regular dy dx derivative is equal to 0. You're going to be finding t values when you do this. And to get the point, you're going to need to find the point on the curve associated with that t value. That's easy. You just plug that t value back into the parametric equations. And similarly, to find vertical tangents, you need to know where your regular dy dx derivative is blowing up to infinity. That happens when the bottom is going to 0. So you find where the bottom is 0 and the top is not. If both of them happen to be 0 at a particular t value, either you have a factor that you can cancel, and you should, and then reinvestigate, or you'll need to use a limit in some L'Hopital's rule. I'm going to show you a simple example, and then I'm going to let you guys go. Find the location x comma y of any HTL or VTL, horizontal tangent lines or vertical tangent lines, for the unit circle. We already know the answer here, but we're going to see that we can discover it like this. So unit circle, x equals cos t, y equals sine t, and 0 is less than or equal to t is less than or equal to 2 pi. Here, dy dx, it's always dy dt over dx dt, is the t derivative of the sine function, or sorry, of the y function, which is sine. So the derivative dy dt is cos t. And downstairs, the derivative of x, dx dt, is negative sine t. So dy dx is going to be 0 if cos t is equal to 0. And sine t is non-zero. So where is cos t equal to 0? And remember, we're just paying attention to 0 to 2 pi. So where is cosine equal to 0 between 0 and 2 pi? Pi over 2, that's good. Where else? Think about your unit circle. Think about the cosine function. Where else is cosine 0? Good, 3 pi over 2. And the sine function isn't 0 at either of those, right? We just want to double check. The sine of pi over 2 is 1. The sine of 3 pi over 2 is negative 1. So we're good here. These are the t values where we have horizontal tangent lines. Horizontal tangent lines occur when t is equal to pi over 2 and t is equal to 3 pi over 2. The associated points there, x is the cos of pi over 2, which is 0. Y is the sine of pi over 2, which is 1. So this first guy leads us to the point 0, 1. And this other guy, when x is cos of 3 pi over 2, that's still 0. Y is the sine of 3 pi over 2, that's negative 1. So the other point on the unit circle where we have horizontal tangents, 0, negative 1. And we already know this. Picture the unit circle. Where are the tangent lines horizontal? At the top and bottom. All right, I know I have we knew a priori that we have horizontal tangents here, and this is 0, 1, and also down here, which is 0, -1. Finding vertical tangents, the same shit. You just got to figure out where the bottom is going to 0 and check that the top isn't. So VTL, vertical tangent lines, will occur when dy dx blows up to plus or minus infinity, which means cos t over negative sine t is blowing up to plus or minus infinity. And that will happen if the bottom is 0. Which happens when negative sine t is equal to 0 and cos t is non-zero. So if we solve these equations, where is sine t equal to 0 between 0 and pi? So negative sine t equals 0 is the same as saying sine t equals 0, which means t is 0 or pi, and cos of 0 is 1, cos of pi is -1, neither of which are 0. So we have vertical tangent lines when t equals 0 and when t is equal to pi. And the points there x is the cos of 0, y is the sine of 0, so that's 1 and that's 0. So this is the point 1, 0. And the other one, this is coming from t equals 0. The other one coming from t equals pi, x is the cos of pi, y is the sine of pi, so that's -1 and that's 0. So the other point here is -1, 0. And this is, again, no surprise. We know that the vertical tangents to the circle are friggin' right here and right here, which are -1, 0 and 1, 0. So the unit circle is a simple example for these things. It's nice because we have a priori knowledge, but we can see that it can be discovered using these new tricks. These tricks work great on any parametric equations. So if you want to find horizontal vertical tangents, you want to find the equation of a tangent line, we can do that. First thing you need to do is practice just sketching the damn things, right? So that's the first chunk of your homework this week. Homework's broken up into 4 pieces, basically. Sketching parametric curves, doing differential calculus, and a little bit of integral calculus with parametric curves. I'll talk about that at the start of class on Thursday. The latter 2 pieces are sketching polar curves and doing some calculus with polar curves. And that's what we're going to talk about next time. Any questions before I let you guys go? All right, I do appreciate your patience here, taking the time to stick around, even though we went a little bit over. Next time, again, polar coordinates. I'll look a little bit more at this parametric stuff. I'm going to show you how to find arc lengths and surface areas in this parametric setting. That's pretty cool. But the bulk of the time on Thursday is going to be devoted to polar coordinates. And then you will be done with Calc 2. Congratulations. Remember, exam 3 is going to be a take-home. I will give it to you on Thursday following lab. It will be due on the day of the final. And that's it. All right. Hope you guys take care of yourselves. Please work hard on this homework. If you need extensions for any past things, now is the time to be getting that shit wrapped up. Do not wait. And yeah, that's it. I'll see you guys on Thursday.
Thank you, Professor.
Take care.